Alright, hey everybody. So we are going to start with a example from scratch on how to do a one sample t-test. Sorry, I gotta draw that out. I gotta write that out. Alright, so what I want us to do, I'm gonna make a little bit of a roadmap here for what I want us to do. I want us to form a hypothesis. I want us to come up with the critical values. I want us to come up with the test statistic. I want us to make a decision. And then I want us to make a confidence interval. And I want us to find the effect size. So we got a lot on our plate for this. We got a lot of work to do. That's okay, because this is exactly what you'd see on an exam. Alright, so let's come up with a fake data set. So let's say that I'm looking at exam scores and I find the following scores. I'm going to make this maybe an easy example because what I wanted to do is, so during the chapter, we used an example where we did not reject the null, and this time I want an example where we do reject the null. So I'm going to come up with some extreme values. So I have 85, 90, 100, 85, 90, 100, and 80, and I am interested, let's say that my my population mean is going to be 70. In other words, what I'm looking at here, these are exam scores. So these exam scores, these are your most recent exams, and I think that y'all did better than my last year's class, where on this exam they had an average of 70. Now, unfortunately, I didn't collect any info about like their standard deviation. I just got something about 70. So that's what we're going to test against. So so I suspect that that our scores are greater than or better than last year's scores. So with that in mind, that should be all the information that you need now to solve all 6 of these steps. So go for it. So remember, what you're looking at is you suspect that these exam scores are greater than this number right here, than 70. So go for it. Pause this video, try to work it out on your own, let me know how you do. So go ahead and pause it. I'm going to count to 3, and then I'm going to start working on it myself. I'm hyped for this. I love this stuff. This is so much fun. It's like solving a puzzle. Alright, so I'm going to break out my calculator here. Okay, so the first, and I don't need a calculator to calculate my hypothesis. So what are we doing? Hypothesis, that's going to be, can I change my pointer options? Yeah, sorry, I just want to change my ink to blue, just so that way it doesn't interfere with all this red stuff up here. And you can see what was here before and what was added. So I know that it's going to have a null and an alternative hypothesis. So if I remember correctly, I'm just looking at whether or not this sample is greater than this. So that tells me directionality. So I would say that x bar, I'm predicting that it is greater than 70, which means that my null hypothesis is the opposite. So my null hypothesis would be that x bar is less than or greater than, or sorry, less than or equal to 70. And boom, there you go. There's our hypothesis. This is what we are testing. The next one, what is the critical value here? What is the critical value for this? So the critical value for this, remember that what we need to know is the alpha value. I did not provide that with you, so let's just assume that alpha is 0.05. So we got 0.05. We need to know the sample size so we can calculate the standard, the degrees of freedom. So I got 1, 2, 3, 4, 5, 6, 7. So my n is going to be equal to 7, which means my degrees of freedom is going to be equal to 6. Alright, so I think that is what we need for the critical. Let's pop over here. So my critical value, I'm changing my p-value to 0.05. My degrees of freedom is going to be 6 because remember it's 7 minus 1. And I'm going to hit calculate. So you can see here the two different values that I have, 1.94 and 2.45. Which one should I go with? I'm going to go with the 1.94. But why? This says right-tailed, so why am I doing that? because this is just a one-tailed test. And even though it says right-tailed, there's a very easy way to get the left tail of that, because actually that's not what we're looking for. We're not looking for the left tail, so we can use the right tail. But if we wanted the left tail, then we could just turn this into a negative, and that would be totally fine. We can turn that to a negative, and that would be the same as the t-critical and the opposite polarity for a positive. Alright, so that is what we're going to be using, positive 1.94. Alright, so I'm going to draw this out right here, down here. So what I am looking for then is that if this is 0, right, so this is a t-score of 0, it's right there on the mean, and sorry, I already forgot what the score was. What was it? 1.94. So I know it's a one-tailed, so I know it's 1.94 because I'm looking for the rejection region above the mean. So we can say that this is 1, this is 2, and I know it's 1.94, so it's going to be somewhere right around here. Was it 1.94? Yeah, okay. Just got it in my head. Alright, so then we're going to be looking to see whether or not our test statistic is going to fall in this rejection region right here. I strongly suspect that it will, because all of these values are greater than 70. But there's a lot of variability here, so we got to make sure that the variability isn't going to make this not significant. So our critical value here, we're going to call that plus 1.94. All right, this brings us to our test statistic. This is by far the thing that's going to cost you the most time, because we need to find the standard deviation, and that takes forever. So here we go. So let's add up all of these and then divide by n, and that's going to give us our mean. So I got 85 plus 90 plus 100 plus 85 plus 90 plus 100 plus 80. And that's going to give me 630 divided by 7. Oops, I screwed something up. 630 divided by 7 is going to give me 90. So again, I'm jotting down over here that x bar is 90. So what am I going to do? I'm going to subtract each of these by 90. You probably already did this. And that's going to give us our residuals. And that's going to be equal to -5 here, 0 here, 10 here, -5 again here, 0 here, 10 here, and -10. Does that add up? Okay, so this is going to be -10, that cancels out. Hold on, I think, is there something wrong here? You know, I'm always psyching myself out. No, this is fine. This works. Yeah, so -5 is 10. It's going to erase this positive 10. This positive 10 is going to erase that -10. That gives us 0. So we are on the right track. Good news, everybody. All right, next thing that we're going to do is we're going to square each of these values. And luckily, we have some nice whole numbers, so that's not going to be hard. So this is going to be 25. It's going to be 0. It's going to be 100. It's going to be 25, 0, 100, and 100. And we're going to add those up. It's going to give me 350. I'm just going to put that in my calculator just in case. I cannot be trusted to do this stuff all in my head. Yes, that is true. It is 350. All right, so then I'm going to throw that into my standard deviation thing. And so I'm going to write out what the formula is first, because I told you I'm doing this all from scratch. So I want you to be able to see exactly where all these numbers come from. All right, so here I'm plugging in some values. The sum of squares is going to be 350 over 7 minus 1, which is going to give me equal to square root of 350 over 6. It's going to be equal to whatever that is. 350 divided by 6 is 58.33. And then that's going to be the square root of that. It's going to be 58.33, which is 7.64. So that is our standard deviation. Cool. I'm just going to make a note of that over here again. So standard deviation is 7.64. 7.64. Someone asked me the other day if any standard deviation this big is common or if that's rare. It's totally common. We've been using a lot of small numbers this semester for our data illustrations. As the bigger the numbers you have, the larger that standard deviation is going to get, and that's totally fine. There's no problem with that. All right, so that's our standard deviation. I'm already going to turn this into the sampling mean, right? So the sampling, the sampling error. So it's going to be S of x is going to be equal to, actually let me write that formula down, S over the square root of n, which is going to give me 7.64 divided by the square root of n, which is 7. All right, so the first thing I'm going to do is get the square root of 7. It's going to be 7.64 over 2.65, which is then going to be 2.88. All right, that is our sampling error. And again, I'm going to throw this in over here. I always like to make these little lists just in case I can go back and plug stuff in. I don't have to search for it. All right, so our test stat. So our test stat, we can plug in this to our formula, our t formula, which if you don't remember is going to be x bar minus mu over the sampling error. So if I plug that in, that's going to be, my mean is 90, my test value is 70, divided by the sampling error, which is 2.88, which will be equal to 20 over 2.88, which is going to be 6.94. So we got 6.94 as our t critical. So our test stat, we would say, is 6.94. Cool. All right, we've come so far, and we are almost over, almost done with this. So, like I said, that takes easily the most time. Excuse me, I got the hiccups. So, is this value, 6.94, is it greater than 1.94? Yes, because if I were to try to draw this out, how far do I need to go? I need to go way over here to get that t-score, which is really, really low, right? That's very unlikely, which means if I were to do this, how do I interpret that? I would reject the null hypothesis. I would say that our scores are not the same, nor are they less than 70. And the implications of that just means that this class is not the same as the class that got 70. There's something fundamentally different about it. They don't belong to the same population because y'all are smarter, is what I'm trying to say here. All right, so that is the decision. So we're going to say we're going to reject the null. All right, that brings us to the confidence interval. So the confidence interval, remember we got our margin of error, which is going to be equal to the t critical multiplied by the sampling error. All right, so how do we get that? We can just plug in numbers, right? So we're going to find that our margin of error is going to be equal to 1.94 multiplied by S of x, which is 2.88. All right, so that means our margin of error is going to be 5.59. Okay, cool. But is that all we do here? No, that's not all we do here. Now we need to add and subtract this from our mean. So our mean, as you may remember, is 90. So we're going to take 90, because the 95% confidence interval, actually let me just I'm going to write this down here. Because the way that we get that number is we're going to take the sample mean and we're going to add and subtract the margin of error. And we already have those values, right? So that's going to be equal to 90 plus or minus MOE, which is 5.59, which is going to give me 84.41, comma, 90.59. oftentimes you'll see these bracketed like that. So we can ask ourselves, does 70 fall within this boundary? It does not. So therefore we can reject the null hypothesis. Alright, so that's our confidence interval. So we would report this on the exam. Cool. Alright, we're making good progress here. Now that brings us to our effect size. So remember, the effect size is going to be equal to D is going to be equal to x bar minus mu divided by the standard deviation. We have those numbers. So that's going to be 90 subtracted by 70 divided by 7.64. It's going to be 20 divided by 7.64. And that gives me 2.62 when I round. And that is it. That is how you solve a problem like this. And it takes some time, it takes some practice, but once you get a hang of it, it's pretty easy. You just got to be careful about how you organize things here. But if you have any questions about how to solve something like this, please just let me know, because otherwise, I will see you for the next chapter. See y'all later.